See? Okay, so this should be recorded now. So, okay, so up until now, we looked at the definition of type theory. So that was, so we have a notion of model of type theory, and that the other name for that was CWF, so categories with families plus some type formers. Because you can have a type theory with pi types, type theory with universes, without universes, type theory with booleans, vectors, and whatever different type formers. So we looked at lots of different of these, and we also looked at the syntax of type theory, which was the same as the initial model. So it was a particular model from which there is a morphism, a unique morphism to every other model. And thus we can interpret the syntax in any model, right? And this interpretation corresponds to, it's the same as when you have an inductive type in Agda or Haskell, you can interpret your inductive type using pattern matching or using the elimination principle of the inductive type. And we also have an elimination principle for the type theory. So elimination principle, this is called recursion or induction, induction or whatever. Sometimes it's called fold and so on. So that's a property of the syntax. And then we also looked at some models. So we looked at the standard model or set model. And this is a very basic thing, because here the standard model doesn't give us much, because everything that we have in the standard model, or everything in the standard model, is just interpreted by its meta-theoretic counterpart. So it's also called meta-circular model, because it's kind of circular, because like function space is interpreted by function space, but the syntactic function space or the object theoretic function space is interpreted by the meta theoretic function space. And that's the only thing, basically that's the only thing that the standard model does. So it's almost kind of the identity model in some sense, that you just take what you have in your meta theory and you just interpret your object theory with that. And in fact, this whatever you have in the object theory, so here the property of this is, so whatever you have in the meta theory, your model will support that. So for example, if we have booleans in our meta theory, then the standard model supports booleans, because we can just use the meta theoretic booleans to interpret the booleans in type theory, or if our meta theory. So whatever our meta theory has, we just get all of those stuff for the object theory. And so if we, yeah, so I mean, Girard calls this Tarskian semantics. So this was the idea of Tarski for logic. He said that I don't know, implication is or conjunction is interpreted by and, right? And that's the most stupid. He called it very stupid semantics, because you just reuse whatever you have in your meta theory, and that's, so it doesn't give much. It's a bit trivial. And so there's a very nice book of Girard called Girard Proofs and Types. It doesn't talk about dependent types, but it talks about simpler types, and it has a nice introduction in the beginning on logic, and that's where you can read about this. And then there's the other kind of semantics, which was called Hayting's semantics, which is much more clever than this Tarskian semantics, which is just some standard thing. And the semantics by Hayting so okay, so it's more clever because it doesn't simply reuse the stuff of the meta theory, but it adds some extra thing. And in fact, okay, maybe I shouldn't have said Hayting, but okay, so Hayting semantics is a more clever version, but now we will talk about semantics which is called Kripke semantics for logic. And for type theory, it's the same. So these are so these are like the Tarskian, Hayting's, and Kripke semantics. These are for logic, so for much simpler things than type theory. And for type theory, we call the Girard or Hayting semantics, in fact. So both of them are called the standard model. And the Kripke semantics is called presheaf model. So we will talk about the presheaf models, which are more interesting. And we've already seen one. So the families model that Raphael talked about last time is a special case. Is a special case of this, and the standard model is also a special case. In fact, special case as well. So families model and the standard are special cases. And maybe before starting the technical details, so the interesting thing about presheaf models is that, so as I said, the standard model inherits everything from the meta theory, right? So if you have some feature of the meta theory, then your type theory, your model of type theory will also support it. And this is also true for presheaf models, as you can see, because, for example, the standard model is a special case. So if you have some feature in your meta theory, your presheaf model also inherits it. So properties of the meta theory also inherited. Yeah, but there is an extra nice thing about the presheaf model that you can so you get some things from your meta theory, but the presheaf model is defined over a category. So the presheaf model starts with a category. We will define this. We will say what this is. And the presheaf model also inherits things from the category. Model inherits properties of the category. So it's a kind of general way to combine things from your meta theory and combine properties of a category. So if the category has some special properties, then the presheaf model will also have those. And this is why it's very fruitful to use presheaf models, because you can they give you some kind of automatic way to obtain some models, because you start with the category, you build in enough stuff, and then you get a model which will support that enough stuff. Some other people call this is also the same idea as forcing for set theory, models of set theory. And some people also call it, for type theory, they also call it forcing. So when you are also forcing translation, there is, some people call this forcing translation, and it's the same, it's simply presheaf models. So these are just synonyms for the same things, the same idea. Okay, so formal, what is the formal definition? So I will say what the formal definition is, and then we look at how we obtain the standard and the family models. Okay, and it starts with this. Okay, so first, the presheaf model has a parameter. So a parameter is a category. So this is the same as a category in category with families. So the C in CWFs, that's a category. So we will denote it by C. So C is a category. So let's just come up with a notation for it. So we have this bar C, which is a set. This is a set of objects of the category. Okay. Then we have Cij, which is a set for every ij in C. So for every two objects, we have a set of morphisms between them. Okay, and then we can compose these morphisms. So if I have a morphism from J to K, and I also have a morphism from I to J, then I get a morphism from I to K. So this is the usual, so you can depict it like this. So if there's a morphism from I to J, and then another morphism from J to K, so let's call this F, and let's call this G, then I get a morphism from I to K, right? I to K, and I denote it the G compose F, as usual with functions. And I also have an identity morphism. So it just goes from I to I for any I. And then we have these left identity law, right identity law, and associativity. So, you know, a category, I think we talked about this before, but a category is just a generalization of monoid, right? In a monoid, you also have a identity unit element, you have a multiplication, and then you have left and right identity and associativity, which are denoted the same. So the left identity says this, the right identity says that if I compose F with an ID on the right, I get the same as F, and associativity just says this, right? And you see, so it's the same number of fields as in a monoid, right? Or it's the same number of operations as in a monoid, because I have a multiplication unit and then the three laws. But here it's more subtle, because, you know, you cannot, in a monoid, you can multiply any two elements of the monoid. But here we can only multiply things, so only combine two things if they match. So if I can only compose two morphisms if their domain and codomains match. And so this is also, so you could, you know, you can also, So a category is a typed monoid, right? Because there are these, it doesn't only have elements. For each element, we have a domain and a codomain. We know where it goes from and where it goes to, and that's how we distinguish them, and we cannot arbitrarily compose them. We can only compose them like this. Okay, so category is a type monoid, or another way to think about it is I'm sure we talked about this before. Is a category is a graph with extra structure. With extra structure, and that extra structure, you know, this is the graph, like objects and morphisms, so vertices and edges, and then you can compose edges, and there's an identity edge for everything, and then these edges also satisfy some laws, right? So you can compose edges, and there are identity edges. It's also called a reflexive transitive graph, right? And with some laws, because the reflexivity is the identity, right? But and it's really an identity. It really behaves like identity, and yeah. Okay. So this is just the parameter of the set of the presheaf model, and then for every model is named after what contexts are mapped to. Okay, so a context in this model. So okay, so in the presheaf model over C, contexts are mapped to presheafs over C. Okay, so what is a presheaf over C? It is the same as a functor from C to set. Okay, so let's make this more explicit. Sorry, it's a contravariant functor from presheaf from C to set. So some people already know what this means, but we will make it completely explicit to understand what this is. So a presheaf has a presheaf C can be defined as a record with 4 components or 4 fields, has 4 fields. Okay, so a category, which was the parameter, had several fields, and now presheaf C has 4 fields. So let's see what these 4 are. So okay, so if gamma is a context, so gamma in this model, if gamma is a context, then it is a presheaf over C. And it has the following 4 components. So it again has this component, which is for each element of C, we get a set. Okay. So it's so gamma gives you, so this bar gamma gives you a family of sets over objects. So for every object, we get a set. Okay. And then we also have a restriction operation. Okay. So what are these usually called? I don't know. So a family over objects of gamma, and this is usually called a restriction. Okay, I write it down and then I make a drawing too. Then it will be simpler to understand. So if you have an element of the family at I, okay, and then you have a morphism from J to I, then you also obtain an element of the family at J. Okay, and notice that so basically we can transport elements of the family gamma using these morphisms in the category, but notice that it's contravariant. So the morphism goes from J to I, and then I can go from I to J, and that's why we use this this kind of notation. I will write some examples in a minute. And we also have 2 laws. So we also have an identity law and the composition law, basically. Okay, and the 2 laws are the following. So if I have a element, if I restrict a gamma with the identity, it's the same as gamma. And if I restrict the gamma with a composed morphism, okay, F composed G is the same as gamma. First restrict it with F and then restrict it with G. Okay, so in fact, these 4 components really correspond to exactly the first 4 components of the category, right? So the category has a set of objects, and for each element of this set, I get a new set. And for each morphism, I get a restriction. And then I should have written the other order. And for composition and identity, I get these laws that this restriction is compatible with composition and it's compatible with identity. Okay, so this is what a presheaf is. And this is the same as, if you know some category theory, this is the same as a contravariant functor from C to Z. And it is also the same as a functor from C op to Z. That's another way to state this. Okay, but this notation is very convenient for describing presheaves. So let's see some examples. Okay, so what if C is so let's see, C is the following category, which has 2 objects, okay, 0 and 1. Okay, 0 and 1. This is the category, and let's call this morphism F between them. Okay, so let's see how this is a category. So the set of objects, okay, so the set of objects is 0 and 1, right? And then we have a set of morphisms. So we have 3 sets of morphisms, right? No, sorry, 4 sets of morphisms, because we have 0, 0, 0, 1, 1, 0, and 1, 1, right? So 0, 0, and so I only wrote this single morphism here, but as we said, there's always an identity morphism. That's one of the operations in the category. So from 0 to 0, we only have the identity morphism, okay? So identity of 0. I can write it like this. From 0 to 1, we have 1 morphism, which is the F, okay? From 1 to 0, we don't have any morphism. And from 1 to 1, we again have the identity morphism, okay? And so these are the objects and morphisms of the category. So we have 2 operations. We have ID, right? We have the ID operation, and we already defined the ID operation, because on 0 this is the ID, so ID on 0 is this ID 0 basically. So ID is given by ID 0 and ID 1, right? These are the 2 identity operations. And we also need to define composition. So there are 3 morphisms, right? 1, 2, 3, and we can compose some of them. So let's see. So for example, we can start with ID 0. Let's see how many things we can compose, and then compose it with F. And that's defined to be F, right? And it must be F because of the identity law anyway. So here we don't really have a choice. We can also compose F with ID 1, right? That's also F. We can obviously compose ID 0 with ID 0, which is obviously ID 0, right? We can also compose ID 1 with ID 1, which is again ID 1. Do we have any other ways to compose morphisms? I don't think so, right? So for F, we can only combine it to this and this. F cannot be, yeah, that's it, right? So we define that, and now we can check that we have all the laws, right? So now you can instantiate associativity. Let's just try to do it for an example. So for example, if I say F, I start with ID 0, then I compose it with F. Oh, sorry, I wrote it in the wrong direction. And then I can compose it with ID 1, right? ID 1. And this should be, associativity says that this should be the same as this, right? We need to prove that this is true, but in fact, by definition of the composition, right, ID compose, the ID1 compose F is just F, composed with ID is F, so this is just F, and it's the same here, right? F compose ID is just F, and then if I left compose F with ID1, I still get F, right? So for this instance, it works, and you can check the other, instances as well, which are all, the others are also quite trivial, like you can do things like F composed by ID0, composed by ID0, and so on, right? So these are all very trivial, and then the only non-trivial cases for the identity laws is these two, which we already defined correctly. Okay, so we can say that okay, this is indeed a category. You know? So in fact, this is what you need to do whenever you want to define a category. You really need to check that it is a category. And if once you've done it for a simple few case, for a few simple cases, you can see you will become quite confident in saying, oh, is something a category, or is something not a category. And let me define another simple category. Okay, so the category which only has one object. Okay, let's call it 0. So this is how I denote it, and if I want to be precise again, then I can write it the same way. So C here is just a set of one object. We only have one morphism. We only need to say what morphisms between 0 and 0 are, and we only have the identity morphism. And right, the only way to compose morphism is to compose the identity with itself, right? And it's just the identity, and the identity is also the identity, right? So identity is given by identity 0, and all the laws hold trivially. So this is another category. Okay, let's call this C prime, this other category. Okay, so we looked at two categories, and now we will check what contexts for these two categories are. Okay, so that is what are presheafs over this category. So what are contexts? Okay, so what are contexts in the presheaf model over C, and in the presheaf model over C prime? Okay, so let's check the C prime first, because that's the simpler one, right? So let me copy and paste the definition of this here. So if C, okay, so C, the context in C prime will have these 4 fields. Okay, so let's see what they are. So gamma goes from, for every object of C prime, we have a set. So for every object of the unit type, basically we have one set, right? So this just means that we have a set, right? We have a set. You know that top arrow set is isomorphic. Top arrow set, in general, top arrow A is isomorphic to A. So this just means that we have a set. Okay, and what does this restriction do? So from gamma, okay, now I replace the unit type, so the set with one element, I replaced it with top. So I have the, okay, let me just write this here. So top has one element TT, okay, and this is how I write in a more type theoretic way. This is a bit set theoretic way to write it, and now I write it with more type theoretic way. This is the unit type, which only has one element. And what does this restriction give me? I can go from gamma TT to gamma TT if I go from TT to TT, but I only have one single thing to put here, right? because I only have one morphism. So the restriction can only be done using the identity morphism, right? So the only thing I can put here is the identity morphism. But I have this law here, which says that if I restrict by the identity morphism, then it is the identity, right? So by this law, restriction is trivial, okay? So I have a family, I have one set, I have a trivial operation, and then I have these two laws which don't get, which I have the trivial operation, which is the identity function. So I might as well forget about this. So basically, a presheaf over C prime has the same data, is the same as a set, right? And and after introducing all the components of the presheaf model, you will notice that the presheaf model over C prime is the same as the standard model. You know, it's some kind of encoding of the standard model. There's always this extra unnecessary information which doesn't give you anything. Like if you have a function and you know that it is the identity function, it's as if you didn't have any function, right? And in this sense, this presheaf model is the same as the standard model. But okay, maybe this example is a bit trivial, but ask any questions if something is not clear. So so let's look at the other one. So what are contexts in the presheaf model over C? Okay, so this was C prime first. In the presheaf model over C, what are contexts in the presheaf model over C prime? So let me copy and paste again this stuff, and then we will look at it in detail. Okay, so what is gamma? So now we have now C is the two object category, right? So C has 0 and 1. It has C has two objects. So in fact, I can replace it with two objects, so two sets. So I have gamma 0, which is a set, and I have gamma 1, which is a set. Okay, so I have two sets. Let's see what I can do with the restriction. So we looked at the category in detail, and we saw that we have how many? We have from 0 and 0 and 1, from 0 to 0 and from 1 to 1, we only had the identity morphism. So that doesn't give us anything because that's the identity function, right? And we have from 0 to 1, we have one morphism F. So the only interesting component here, the only interesting thing is this one, when I use here the F morphism, which goes from gamma of so F, let me just copy this. So F goes from 0 to 1, right? So then this needs to be 1 and this needs to be 0, okay? So the restriction goes from 0 to 1. And again, as I said, the identity, for example, the identity on 0, it will go from 0 to 0. It goes from gamma 0 to gamma 0, but because of this law, it has to be the identity, so I don't consider this as an interesting component, okay? And these are also just some equalities, but they are completely trivial here. So in fact, these are not very interesting components, okay? So maybe I just leave them here, but saying that these are not interesting. So in fact, this model, so contexts in this model have these three components, so two sets and the function between these two sets, right? The only thing I should have written it this way and then instantiate it with F. And then I have a function from gamma 1 to gamma 0, right? This is the only restriction I have. Okay, so what I get is two sets and the function between them. And with this, I think Raphael said it last time that this is the same or equivalent. This is the same as the families model. Right? Let's just look at this again in more detail. So I have so in the families model, con was in the families model, con was a gamma 0 set. Let me write a notation which will be helpful, and or maybe I should just call it A. Okay, an A set and a B, which is a arrow set. Right. This was the families model. So set and the family over it. That's why it was called families model. But this contains the same data, because you can check that if you want to. Oh, sorry, there was a question. So gamma 0, in presheaves, you have a family of sets over the objects of the category. So for every element of the category, you have a set. So now we have two sets, right? We have gamma 0 and gamma 1. It depends it's a notation if you write it in lower or upper index, but I would write it this way, in fact, because you see here, wait, where did we, here we said, sorry, where did we define presheafs? Yeah, here. So in a presheaf, for every object of the category, I have a set. And here, if my category has two objects, then I have two sets. Okay, and in fact, two sets and the function between them is the same as a set and a family over that set. And this is a very good exercise. So it's an extremely good exercise to prove it's an equivalence. So let me just show you some part of this proof. So let's say we have a gamma 0, gamma 1, and a function, okay, this f between them, and then we want to obtain an A and a B, okay? So it's, how do we obtain the A and the B? So the A will be just gamma 0, okay? It's just gamma 0, and the B is, so for any small gamma in gamma 0, oh, sorry. So for any small gamma in gamma 0, gamma 0, I need a set, and I will say that I want the elements of, I don't know, omega, which are in gamma 1, such that if I use the function, what's going wrong here? Oh, if I use the function goes from omega gamma 1 to gamma 0. So if I use this function on omega, then I get something in gamma 0, and I get the same as this. Okay. So let me do some drawing. So here I have gamma 0, and I have the set gamma 0, and I have a set gamma 1, and then I have a function from gamma 0 to gamma 1. Right, which is called restriction by f. And in the other case, I have a type A, and then I have the corresponding thing is that I have a B over it. Okay, so B is an A arrow set. And then I just say that when I want to convert from this representation to this representation, then I just say that B are the elements of gamma 1 which map to gamma 0. Okay. So this is this conversion, and the other other direction is even simpler. So what if I have a B, and then I want to map to sorry, I don't know how. What do I map to? So I again choose the A to be at the bottom, and then here I need another set, but I only have a set B, so the set will be A in A together with an element of B of A. Okay, that's the set. I need more space. And then, so that goes up there, right? This is the product of sigma type or product type element of A and two or dependent product. So an element of A together with an element of B at that element, and then I can go from this product type down here, which and it's just first projection, right? So by first projection maps gives me from an sigma AB. In Agda, you can write this as sigma AB. This is the same. You get an element here. Okay, and then so now we define the two directions of this map. So how to map from the family context in the family model to a context in the presheaf model, and how to map from a context in the presheaf model to a context in the family model. And to show that this is an so-called equivalence, you need to show that if you start with an A and a B and then go here and then come back, then you have an isomorphic type or an isomorphic set. And and then if you start with this and go here and then go back, then you again get an isomorphic object. Okay, so that's I leave this for homework. Okay, so homework. Prove that A, B, and then you get this, right? And then you get something, and something is isomorphic to A, comma B. Okay, so what is an isomorphism between to a set and a family over it? It's so you first need to think about what does an isomorphism between these two such objects mean. So what is what is an isomorphism between AB and A prime B prime? Okay, it's the logical definition. You have a function between A and A prime, which is a bijection, and then you have a bijection for B as well over the bijection for A. Okay, so this is already an interesting thing to do this, and also in the other direction, right? So you start with gamma. Let me just copy it. So you start with this, then you map it to what? To this. This, and then you map it to something, and then again something is isomorphic to this thing that you started with. Okay. Okay, so this is the exercise. Okay, so what did we do so far? I told you what categories and presheafs are, and I just stated that in the presheaf model, the contexts are given by presheafs over a particular category. Okay, so we had so there are lots of presheaf models, as many as categories, right? So each category induces a presheaf model, and then a context in the presheaf model for the at this particular category is presheafs over C. Okay, and presheafs are just a technical term for these four kind of components. Okay, and then we checked that for C and C prime, so the two object category and with one morphism, right, between them, and for the zero object category we obtain for con the same as in the families and standard model. Okay. Okay, but so far we only looked at what contexts are in the presheaf model. So let's look at the other things. So let me just copy, okay, the rest of the presheaf model. Okay, let me just copy contexts again. So these were contexts. Oh, sorry. Okay, so these were contexts. It has these four fields. So let's see what is a over a tie gamma. Okay, and at least for me, the simplest way to think about this is just to define this component-wise as well. So now A will again have four fields, but they will be named by A. So let's see. So A is not simply a set over C, but this is how so it's not over C, but you know it also needs to depend on gamma because we have dependent types. So how do we do A? So we say that for any I in C and for any gamma at I get a set. Okay. So maybe even before describing, so this is not good yet, but even before describing this, let's see the family in the families model. What do I get? So I get A0, which is gamma 0 to set. Okay, this here this is 0 is an implicit argument, and then I also have A1, it's gamma 1 RO set. Okay, so kind of in the families model, I have, right, for each I have for each context I have an element. I have a set at set gamma 0, and I have a set gamma 1. And for each type over that context, I have a family over both of them, right? It's kind of, it's like having two copies of the standard model, right? Because I have two types, one over gamma 0 and one over gamma 1. Okay, but that's not everything, because this is just an example. So in or over C, I have this, but I also have this restriction now, which will go between the corresponding components of A. So let's see. So if I have an A at I and gamma, okay, let's type check this. So gamma, right? It's in gamma of I. So small gamma is in big gamma of I. And then if I have a morphism from J to I, let's give it a name F, then I have an element of I at J, but now here I need to write something of type gamma at J, right? Because AI here is over gamma at I, and then if I take AJ, then it's over gamma at J. So I need to write here something of gamma at J. And the small gamma is at gamma at I, but I can just use the restriction for gamma, right? So I just say, I start with gamma, which is gamma at I, and then I use this operation, which goes from gamma at I to gamma at J, and I restrict it to this. So you see that the A bar depends on the gamma bar. The A restriction depends on the gamma's restriction. And again, I have the same same equalities here, which are, again, if you want to type check these are dependent. Sorry, I misspelled this. I wanted to write here gamma, small gamma. Okay. Sorry, let me fix it here as well. So here I wanted to write small gamma because this big gamma doesn't make sense here. So here. Okay, and even here. Okay, so yeah, and okay, let's type check this. Okay, that this really makes sense, this equality. So alpha is in A of I of gamma. Okay, and then if you take alpha ID, then it will be, by this law, it will be A of I substituted by, or restricted by ID, right? This will be gamma ID, but I know, because of this law, that this type is equal, sorry, how do I, this type is equal to gamma, simply, right? Because gamma ID is the same as gamma by this. So again, this equality depends on this equality, but that's expected because we have dependent types, and all components of types depend on the components of context. And the same happens for composition. So gamma is a presheaf over C, and a type in gamma, this also has a name. This is called displayed or dependent presheaf gamma. Okay. So this notion of displayed presheaf, it makes sense, and this thing displayed it or dependent, it has a meaning in general for every algebraic structure. So not only for presheaves, but it also works for everything else, for lots of other things, not only presheaves, but we also have displayed categories and I don't know, displayed for displayed groups, displayed rings, and so on. Okay, so we discussed what are contexts and types in this presheaf model, and I will tell you about, okay, so what will be the substitutions. So what is sub gamma delta in the presheaf model? So you could also say it could have 4 fields, but the situation is simpler because we don't need to say anything about equalities. So this is so here I have first give it a name. So this is what they call, if you know that presheaves are just functors, then there is a in category theory there's a notion of map between functors, and it's called a natural transformation. So this is a natural transformation from gamma to delta. But you can also, if you just look at these two definitions, it's very straightforward to define what do you mean if you have a gamma and a delta with these 4 components. Sorry. So what is, if you have a gamma and a delta with these 4 components, what is the map between these 2 things? So first you need a map between gamma and delta. So that's quite simple. So you want to go from gamma to delta, right? Delta. But the gamma and delta are not sets, but family of sets. So what you say is that for every I in C, you get a map from gamma I to delta I, right? Gamma I and delta I are sets, okay? So we just set for every I, we have a function, okay? And the second component will say something about these restrictions, okay? For each restriction, we get some equality, so we can apply this function in two different ways. So let me draw it first. So, okay, so if I have a gamma I, then by such a sigma, right, sigma, I can go from gamma I to delta I, right? But I also have these restrictions. Look, this restriction goes from gamma I to gamma j. So I also have this. I can go from gamma I to gamma j using this restriction by f, okay? So I just write here next to this drawing that f is in Cji, right? F was in Cji, then I can go from gamma I to gamma j. Okay, but now I can also apply sigma on this gamma j, right? Because, because sigma, I don't know why Emacs does this, but okay. So sigma works for every I, so it works from I for gamma I, and it works for gamma j as well, and then I get a delta j. I can use this restriction also for delta, so I can go down here with restriction at delta, right? We have the same notation here, but you know, here I didn't write that this is a restriction for gamma, but if you want, you can write a gamma afterwards or something like that, and then you know that this is restriction for gamma. Okay, and this equality says exactly that this diagram commutes. So if you start here and go here and then go down here, it's the same as going this way. Okay, so this is like a preservation. So here we will say that sigma preserves restriction. Okay. This is what this says. So let's just state it. So if I have a small gamma, which is in gamma I, then I apply sigma to it, and I get something here, and then afterwards I restrict it. Then it's the same. So this was at I. It's the same as first restricting gamma. You see, now I'm going down from here, and then applying sigma to this. But because this is already at j, then I'm taking sigma at j, okay? And this is what this naturality condition says. And for those, okay, so this is a substitution is this natural transformation. This is what is called naturality. And this is like, you can think about this as a polymorphic function. So if you want to learn category theory and what natural transformations are in category theory, then the best, or the first intuition for natural transformations is kind of polymorphic functions in functional programming languages. And in a polymorphic function, it works for every type. It has something like this. And then polymorphic functions are natural transformations. So the similar equalities are also true for every polymorphic function in Haskell, say. Okay, so these are parametrically polymorphic functions and not ad hoc polymorphic functions. Okay, so but this is just for those who want to understand what natural transformations are. I just write it here in a comment that okay, let me just put it here. Natural transformations are parametric polymorphic functions in type theory are natural in Haskell are natural transformations. Okay, this is just a comment for natural transformation. Okay, so we discussed what contexts are. So contexts are presheaves. So they are families of sets between which we can we have these maps. Sorry, I promised to draw put a drawing here, which I forgot. So let me just draw it here. So if I have the here below, I have the category C, right? It has objects and morphisms between them and so on, like here, for example. And I have a lot more morphisms and whatever. Maybe I also give this a name. And then if I look at gamma, then gamma will give me a set for each object. So here I have, okay, let me try to draw a set. So this will be the set for I, okay? Okay, so this will be the set. Sorry, how do I write it? This is the set gamma I, right? It is over I, and it will have lots of elements like small gamma and small gamma prime, okay, and this kind of elements. This is just a set, and it has functions and okay. And I also have another set over gamma j, right? This will be gamma j. It has some other elements. I don't know, omega prime, okay. And I have for each object I get a set. So also I have a set over gamma over k, which is gamma k. Okay, so I call this I don't know, beta prime. These are some elements, okay. So so I described the set, and then I have this restriction. So for each morphism, I can go in the other direction between this set. So for example, I have a function from this set to this set, and it was named restriction by f, right? So this function, okay, space here between these sets, okay. So this function goes from this restriction f goes from gamma j to gamma I, right? If f went from I to j, but sorry, to make match with the what I wrote here, I should make f go in the other direction, okay? And then the restriction goes in this way, right? And then it matches the notation here. So the restriction goes from gamma I to gamma j, right? So for each morphism here, I get a function here. So if I had another morphism here, say, then I would get another function into this direction, right? And so on. And here again, I have another function, right? So here I also have a function which is a restriction by space. So here I have restriction by G. And I also have the, okay, and what do I know? I know that I can, yeah, okay, so G went now this way. And I know that I can also compose these functions. Okay, sorry, let me change the direction of G because otherwise it doesn't match what I wrote there. Okay. And sorry, it also doesn't match because of this. Here I just changed the notation, but yeah, it means the same. And now it will match what I use in the drawing. So I can compose f and g, and then I get a function from gamma I directly to gamma k, and this is what I write it as f compose g, right? First I go with, sorry, what's wrong? Yeah, g compose f. Yeah, first I go with f, and then I go with g. And then this equality says that going from this set to this set in 2 steps by first using this function and then using this function is the same as going directly using the composite function, right? Using the composite morphism, because I have composition in the category. Okay, and also I have this other property that, you know, I can always go from here to here. Right? Just by using the identity. And then it doesn't do anything, right? This just says that this doesn't do anything. It just leaves everything as it was. So I can use the identity here. This was just the identity on K. So there is a morphism from K to K. This is a loop, right? It's a loop arrow which goes from K to K, and this is identity, right? And that leaves it like that. So in the context in presheaf model are these families, are these sets, right? There I have lots of sets instead of just one set, as in the standard model. I have lots of sets, and I also have maps between these sets, and these maps are prescribed by the category. Okay, and obviously, I also have some laws how these maps should behave properly, so that they should preserve composition in the category, and they should also preserve the identities in the category. Okay, so that's how you can think about the presheaf graphically. And then you have dependent versions of these. You could also try to draw these. It's a bit complicated, okay? And then we also have natural transformations between these presheafs. So now if I have one of these, and then I have another one, okay? So if you can depict the natural transformation by having 2 such things, okay? I have one of these, and maybe I can draw another one above it. Maybe I can draw it cheaply. Let's try it. So how do you depict the natural transformation? So what if you have a gamma, okay? And now I not only have a gamma, but I also have a delta, okay? So I replace the gammas with deltas. Okay, right? So I over C. Now I have 2 presheafs, the gamma and the delta. And a transformation from and a substitution from gamma to delta, it basically gives me a function, right, from this set to this set, and another function from this set to this set, and so on. So let me draw these. So for example, I have this one, okay, and this is what I call sigma at I, right? So I can go from gamma to delta, gamma I to delta I with this function. And then I also have, sorry, I need a bit more space, or, so I also have another function here. Sorry, what did I do? Okay, this is gamma J, and then I have another function here. This is gamma K. Right? And then the naturality says that if I go up and then go right, it's the same as going right and then going up, right? That these functions are also compatible with these morphisms in the category. Sorry, was there a question?
Yeah, sorry, I just wanted to mention that I think you should write F compose G in that diagram, because it's contravariant. So the bottom arrow from gamma I to gamma K should be, I think.
Oh yes, yes. Sorry, where was the first? Here. Yeah, sorry. Yeah. So G was the first.
That's good. Yeah, and the diagram, I think it should be flipped.
So, but wait, I also need to flip here, no?
Well, yeah, you could.
Okay, sorry. Yeah. So first I go G as here, and then I go F, right? So then this is also flipped. Okay. And where did I mess it up? So here, is it okay? First goes the G, then the F. So here it was okay. And here I also need to fix it. So here it's F compose G and F compose G. Okay. Is it correct now? Yeah. So if you draw this down, then it's very natural. Like all of these definitions are very straightforward because that's the only meaningful way to give. So presheaf is fixed. We can't like you could define that. It's a good exercise if you just write down what a presheaf is and try to derive the rest of the model, and then you don't really have a choice. This is what you need to put there for the rest of the model. Okay, so these maps between presheafs like are these kind of maps which are natural, so that there are these squares and they commute with these squares, and that's what we said for substitutions. And then just quickly, what are terms? So terms are just dependent versions of these substitutions. Okay, so a term between gamma and A is a kind of dependent natural transformation from gamma to A now. So let's see, the T component now doesn't go from gamma, it goes from gamma I again, but it doesn't go to delta I, but it goes to AI. But AI has this, let's see, let me just put here the type of this. So what is AI? So A doesn't only depend on the object of the category, but it also depends on gamma, witness of gamma at I. So here I need to also write a witness of gamma at I, but here I have it. So this is the input. So these are just dependent functions, right? So these are for substitutions, I just had non-dependent functions, right? Where are they? Here, this is a non-dependent polymorphic function. For every I go from gamma I to delta I, and here is a dependent version of it. Okay, and I have the same equality. Okay? And this equality makes sense, and it again depends on the it depends on the restriction at A and the restriction at gamma, right? So here I use the restriction at A. So this restriction is at A because T of gamma is in A, and I can restrict it in A, or I can restrict it in gamma. So here I restricted it in in gamma. Okay. Oh yeah, this was the reminder here. Okay, so in short, so contexts are presheafs, types are dependent presheafs, substitutions are natural transformations, so natural maps, natural polymorphic functions which satisfy some equality, which are natural. You can think about this, and then terms are just dependent versions of them. And then natural transformations. Okay, and it is easy to derive the substitution calculus. So calculus, you know, we so far we only said what the sorts are, but we need to say, you know, do we need the empty context? We need context extension. No, we need the P substitution, which goes from gamma A to gamma. We need the Q term, which goes from gamma A to AP. And oh yeah, we need first I should have written, we need substitution as well, right? So a type in delta, substitution from gamma to delta, then I get a type in gamma, and we also need substitution for terms. sigma. Okay, and we have all the equalities, and these are all very easy. So this is a homework. Okay, homework. Let me just show you some small part of it. So, for example, this it will be it's some trivial presheaf, which is just the unit set. So this, it doesn't depend on its context, right? For every I is just stop. Okay. And then the restriction is then completely trivial, because if we restrict the single element of TT, we just get TT, okay? It's trivial. Okay, and let's see how context extension works. So gamma is right, it goes from C to set. So the first component of gamma is just a set for every element of I. So, and I have an I here, so I can take gamma I, which is a set. Okay, and now what is A? So A is a, right, so for every I and every gamma I have a set. So this will be just sigma type. So sigma type of this small gamma and A at this small gamma. Okay. So context extension is just sigma types, and then you can define restriction works. Restriction works very easily, in fact. So if you have some element of this sigma type, okay, some gamma here and some alpha, and then if you want to restrict it by F, you just do it pointwise. Okay. Yeah. Check it. So, and then you can define all of this, the rest of this stuff, and they are all very simple. So I think the only way to learn it, okay, I know two ways to learn this. One is to learn lots of category theory first, and then you can just realize what these operations are. They are just some trivial category theoretic things. That's one way. The other way is just to try to define it, and then you will see that there's only one thing that you can write for all of these operations that satisfies all the laws, and they are all very natural, and it's a good exercise to do it. Okay, check it, just do it. Do it. So homework, home. I mean, it doesn't make sense doesn't make too much sense for me to show it here. This is something that you have to do yourself. Or I mean, it probably would make sense to now go in a circle, and everyone who's listening should define one of these operations. Yeah, or something like István does it at his type systems tutorials. No, that works very well.
I mean, sometimes it.
Yeah. Yeah, but yeah, and also I think I think it probably makes some sense for you to watch me do it, but I think it's not very time efficient, because you could also do it in a bit longer time, and you would also learn a lot from it doing it, and you learn much less if I do it myself. Okay, so yeah, okay. But okay, we will see how much of these operations we need. Let me just show you some little more. For example, what is a substituted type? So for a substituted type, here there's always an implicit argument, add some object of the category, and then add the dependency at the context. It's just we take A, and then we just use we just substitute gamma. Okay, so it's basically composition, and it's the same for terms. So for terms, you can write exactly the same thing. Okay. Okay, and let's just see what P and Q are. So P is just as usual as it was in the standard model and the families model. You've already seen this. P of gamma alpha is just gamma, and Q of gamma alpha is just alpha. Okay, and you can check that the laws hold. So these are all very, very simple. Okay, is there anything? Oh, the identity and the comma. I wanted to. So what is? I just write it here because this might. So identity is just identity. Identity composition, like in the set model, is just composition. So I take. Sorry. The action of sigma and then the action of delta. And okay, and then the one thing that I forgot is this one. So what is sigma comma t at gamma? It's just pointwise. So I take sigma at gamma, and then I take t at gamma. And the nice thing is that once you do this, right, once if you define the standard model or the families model in Agda by hand, it's a lot of work, but it can be done easily. But now if you do the presheaf model on paper, okay, I don't recommend to do this in Agda. I recommend to do this on paper. If you do this on paper, then you get lots of models, right? Because for each, you didn't only define one particular model, but you defined a huge family of models, because for every category, there is a presheaf model. And you defined all of these at the same time, okay? So, okay, so for every category, we obtain such a model. Okay, so so I said in the beginning that presheaf models can do two things. So in presheaf models, I get everything from the meta theory. Okay, so for example, if I have natural numbers in the meta theory, then presheaf over C supports natural numbers as well, right? For any C, no matter what the C is, I will have natural numbers in presheafs over C as well. And they are defined pointwise. So that's very simple. So let's just look at natural numbers for a second. So natural numbers are a type in any context, right? And moreover, I even have this, that if I substitute natural numbers, I get not again. And 0 is a term in any context of type not, and successor, let's write it this way, takes a term of gamma of type not and gives you a term gamma of type not. Okay, and then I also have some recursion principle. And you can define natural numbers in the presheaf model by saying that not at gamma is just, right, here is this is a set, a type. So it has the first component, which is the family of sets. And I say that every family is just the meta-theoretic natural numbers, okay? And what does restriction do? Restriction doesn't do anything. So if I have a natural number and I restrict it, I return the same natural number. There is no, so you see here is, there is no interaction between C and the natural numbers, right? Just natural numbers are just defined as this is called a constant. This is the constant and presheaf. Whatever the element of this is just natural numbers. And then you can also define 0. So 0, and for any gamma, it's just the constant 0, right? So this needs to be an element in this. If this is the argument I here, then it needs to be in this, but this is just the meta-theoretic natural number. So you just use the meta-theoretic 0, right? Again, successor of t at some gamma is just 1 plus you take the interpretation of gamma, which will be a meta-theoretic natural number, and then you get a one larger number, and that's how you get a bigger natural number. And okay, and you can also derive the recursion principle. Okay, recursion. We'll state what the recursion does and do it. Okay, maybe let's just do the recursion. Okay, so because this is a bit bit more okay, it has some details, but okay, so what does recursion do? If we have a type A, and then we have a Z, which is a Tm gamma A, and then we have an S, okay, which is a Tm gamma extended by A, and it has type A. Here I need to weaken this type. Then from a natural number, I get the Tm gamma A, right? This is how it is this is the most convenient way to define what the recursion does. Okay, so you can think about this. This is a natural number algebra, right? Or like it's something which has the shape of the natural numbers in general, right? Because there's a set which has an element and there's a end of function on that set. I could have written here function space, but I haven't defined function space in the presheaf model yet, and I can just use context extension to express this dependency, right? So the idea is that this is the same, right? This is the same as a Tm gamma AROA, right? But, now I want to use this one because I don't have the function space yet. I haven't defined it, and then I get for every natural number I have an element of this, right? And I have the the definitional rules are that if I apply this to 0, I should get back Z, right? And if I apply this to successor of some t, then I use S. Then it's like S, and then using then having a recursive call at one smaller object. But now because S is in this extended context, then and it's not a function like here, so I don't use here function application, but I need to substitute this by id comma this, right? So id just gives me this gamma component, and the recursive call gives me another a, because the recursive call gives me a Tm gamma A. Okay, so this is the definition of the recursion principle for natural numbers, and now let's see how you can implement it in the presheaf model. So you have rec a z s t, and again you have a gamma, and you need a Tm gamma A. So you need something A gamma, and just as here we used for 0 we use the meta-theoretic 0, for successor we used 1 plus. Here I will need to use the meta-theoretic recursion principle of natural numbers. So let's see, I have so A at gamma is a set, right? Z at gamma is an element of A at gamma. And what's the type of S? Let's see, what's the type of lambda x, S gamma comma x? Because S depends on a gamma and an A, and as we said, context extension here is a sigma type. So the interpretation of S, sorry, let me write the interpretation of S first. It's gamma at some I. Right here there was a implicit argument I. So it is gamma extended by A I. Sorry, what did I write? R rho is because it is a term, right? It has this. Then it goes to A I. Sorry, let's call this gamma. Or let's call this gamma prime. This is AI at let's do it slowly, at gamma prime. And I mean, it takes some time to get used to these calculations, but if you defined all of these, then you will be able to this, because look, substituted type is defined like this. So AP makes the P come here. So now I use A at P of gamma, and then P of, what does P of gamma prime does? It just uses first projection, right? So here, this will be just first projection, but this only type checks because I know that gamma extended by A was defined, as we saw it up here, by a sigma type. So this is the same as as a small gamma in gamma at I times A at that small gamma, right? Yeah. Okay. So this is the type of this. I uncurry it, or if I curry it, then it's a bit more readable. So it takes a gamma, and then it takes an A at gamma, and then it returns a gamma. Right? So this is now the curried version of the same, more readable version. So this thing gives me, so if I write this and I give a name to this, I call it X, or let's call it alpha, because that's what we called it before, then this will be a function from A gamma, sorry, this is an implicit argument, A gamma to A gamma, right? Okay. So now I look at what is generated by this data. You see, this is a meta-theoretic natural number algebra. So I have a set with an element and an end function on it. So I can just use the meta-theoretic recursion principle. So it's the recursion principle for natural numbers, and I give it this particular set. Okay. And I give it this particular 0. And I give it this particular function, successor function. Successor, and then I need to give it a natural number, right? And this, which will be just t, which will just be simply t gamma, right? And then I get an element of, and that's what I needed, okay? And then naturality. So for all of these operations, naturality needs to be checked, okay? Naturality needs. For zero and successor, naturality is very trivial because I defined restriction by just constant function, so it doesn't matter. Here it's a bit more subtle because I need the naturality of A to prove naturality of recursion. Okay, naturality needs to be checked, and computation rules. Checked. Computation rules are very easy. Like imagine if you put 0, if you put 0 here for t, then this becomes, by this definition, this becomes 0, and then I really get this one back, right? And you can also see that successor is defined as 1 plus, So if the meta-theoretic recursion principle has the proper computation rule, then the object theoretic natural numbers recursor also has the proper computation rule. Okay, so this example here of natural numbers, it was a so this is was the example that once I have something in the meta theory, I also have it in the object theory. Okay, in presheafs for that presheafs over C for any C. Okay, and this method works. Okay, so this method works for all other type formers. So I don't know, vectors, works for inductive types. It even works for, I don't know, did we talk about it? Even works for quotient types. Binary trees, whatever, infinitary, like infinitely branching trees, and so on. Okay, so it works for all kinds of type formers. Okay, all kinds of like inductive types. And inductive types. So these were all inductive types in the inductive definitions in the meta theory. It also works for co-inductive definitions. So for example, it also works for streams, infinite lists. So if the meta theory has infinite lists, then the presheaf model also has infinite lists and other stuff. Okay. Okay, but we haven't. So for every model, before we first, I think one of the first type former that we defined was always pi types. So we will define pi types soon, but a bit simpler are sigma types. So let's do sigma type first. So sigma types over C. Those are also pointwise. Okay, point. Well, pi types and the universe, these are a bit harder. Okay, these are a bit harder. So the presheaf model also has pi types and universe, but it's a bit more difficult to define them. And I guess streams are also a bit more difficult to define as well, just as pi types and the universe. But let's see sigma types. So, right. So how did sigma types work? So for a type in gamma, and then a type in over gamma A, I get a gamma. This is how sigma types are defined, and then sigma AB has two components, right? For every object of the category, and for every gamma in gamma at that object, I need to give a set, and that set will be just the meta-theoretic sigma types. So here I use meta-theoretic natural numbers, here I use meta-theoretic sigma types. So I have a gamma in gamma at I, and sorry, I called it A at gamma, and then at B at, I should have called this alpha, B at gamma comma alpha. Okay, so it's very similar to context extension, similar to the interpretation of gamma A, right? That was also a sigma type, but here the A was already a dependent type and B was a dependent type over it, and here gamma was just a presheaf and A was a dependent presheaf, so that's the difference. And then the restriction is also pointwise, just as here. So if I have an alpha and alpha prime, and I want to restrict it with F, here I'm restricting at sigma AB. it is the same as as taking the pair of restricting alpha by F, and I restrict at A, and here I restrict alpha prime, and I restrict it at B. Okay, and the laws for you know, this law, for example, this identity, it needs to be the same as alpha comma alpha prime, and this holds because this is just defined pointwise. So I restrict at A, and I restrict that by ID, and I restrict at B, and because for A and B, I have that this is equal to alpha, and for B, I have that this is equal to alpha prime, then it's component-wise equal, so the whole thing is equal. And this is how I can prove. And similarly for composition, because composition law holds for restriction by composition, is the same as two restrictions. It holds for A and holds for B, then it holds for sigma AB. Okay. So this is how my model, presheaf model, has sigma types, and pi types are a bit harder. So this is what, if I don't know if any of you, maybe it's probably not helpful, but this is also called in logic. In logic, they call it Kripke function space. Possible in Kripke semantics is also called possible world semantics, and in this possible world semantics you also have implication, yeah, and this is defined like implication possible world semantics. Okay, so if you wanted to define pi A, okay, so pi AB, is not completely straightforward, because you could do this. I mean, this would be the, okay, let me just write down this stuff here. Okay, sorry for sigma types, you know, you also need to define the comma operation, and you also need to, yeah, so homework. Need to define the comma operation and the first projection and second projection, and you have two beta laws and one eta law. These need to be, and also the substitution laws, right? So these need to be proven. We haven't looked at these, but these are simple. Okay, so here there are lots of details all the time. This is typical for type theory, that you always have lots of details, and you can either, yeah, again, there are two ways to deal with all the details. So you either learn lots of category theory, and then you use some very generic theorems from category theory that kind of fill in the details for you all the time. But then you need to work very abstractly. If you want to work a bit more concretely, then you need to do the work and fill in the details for yourself and really check that these things work. But also, even if you do it the categorical way, I think you need to fill in lots of details in the beginning when you learn category theory, and then later you just remember that those things work and you can reuse them. So in fact, there's not that much difference between the two approaches. Okay. So let's go for pi types. Let's go to pi types. So again, the pi has the same. It has the same type as sigma type, so it takes two types, and type A and another type over it, and it gives you a type. And the straightforward way would be just saying that pi AB is now, okay, so I can take A gamma, which will be a set, and this will be a dependent function. So if I have an alpha in A gamma, then I could return a beta in gamma comma alpha. Okay, so this you could use this definition. You can also define restriction for this kind of stuff and a lot more. But the interesting thing is that here, okay, so this is this is interesting that here I told you that I don't do this. This is very straightforward and you can do this. But if I said the same thing here, then I would be lying. So if you define pi types like this, then something will go wrong. And in fact, it will go wrong quite late. So I think you won't be able to define application or lambda, but pi is fine, the substitution law is fine, and lots of things will be fine, but something will go wrong. So so in fact, for pi, this is the wrong definition, even if this would be this seems to be the most straightforward definition. And okay, so to convince you why this is wrong, we could give some counterexample. Or we can also derive the natural net definition with some more advanced tools that we will probably discuss at the next seminar. But maybe what I will do is just to show you the right definition and maybe try to give some intuition for that. So the idea is that if you want to go from A to B at I, it is not enough to be able to go from A to B at I, but you need to be able to go from A to B at everything which is after I. So what do I mean by this? The definition of pi is like this. So for any, let's say, so for any J, another element of the category, and for any morphism from J to I need to be able to go from A at J, okay? But now gamma is at I and not at J, so I need to restrict gamma by this F to be again at J, okay? And this is the idea of this Kripke function space. So in this function space, I say that I don't only have a function from A to B at I, but I need to have a function from A to B at every J from which I have a morphism to I. Okay, and oh, sorry, I should have given this a name because I used it. So this is called F. So for any F, I have a function from A to B, and I'm not yet finished, in fact, with this because I will need something else. But so I think the usual way to explain this in logic is that, so implication has an interesting interpretation in logic. So this Kripke semantics, in fact, this and presheaf semantics is called this possible world semantics. So, which means that for every here we had the picture. So you can also think about this. So for every object of the category, I have a set. Okay, and in this possible world semantics, C is viewed as the set of possible worlds. So I is a possible world, and J is a possible world, and K is a possible world. And you think about logic. In logic, you can prove things, just as in type theory, you can prove things. And you know, types can be viewed as propositions or theorems and or predicates, and then terms can be viewed as proofs of the particular type. So in presheaf model, we have different worlds. So and there is a at I we have an interpretation of some type gamma or some context gamma, And this interpretation of I at gamma will say that it says what is true in the world I, okay? And this is another world J, and maybe some other things are true in the world J, and maybe some bit different things are proved in K. And then these morphisms give the connections between the world, and one way to think about these connections is time. So if there's a morphism from J to I, it means that J is later in time than I, okay? So if something is true in I, that's what it means that I have a witness gamma of gamma I, then it also must be true at a later time, okay? So in logic, this possible word semantics or this constructive semantics says that you know, in constructive logic, there's no Platonic world of true things. Like, it's not true that everything is either true or false and it's already determined, but proofs have to be constructed. And right now, at one stage of time, at I, maybe some things are true, okay? And maybe at a later time, more proofs will be constructed. So the humans prove more things, and then we will have proofs for more stuff than right now. But it cannot happen that something is true now, and maybe in the future it won't be true anymore. Because if you constructed a proof today, then that proof will be valid for any later time. And this is what these morphisms make sure, and these restriction operations make sure, that if I proved gamma at I, and J is later than I, then gamma must be true in J as well, okay? And this is an intuition, this possible world story, and then implication is interpreted, or pi type, which is a generalization of implication, is interpreted by saying that you only have a witness, so you can only prove that A implies B, if for every later world A implies B, okay? Because for implication, you need to make sure that if you just prove that an implication is true today, then there might be a contradiction in the future. So you need to make sure that if you have an implication, if you proved an implication, then it can be reused in any proof in the future. So so you will have a proof also in the future for that, and that's how this is expressed. Okay, and we're almost done, but let me just finish this definition, because this is really the definition of Kripke function space for proofs, and for that this would be enough. But now we are in type theory and not logic, and type theory can do more stuff than logic. So we not only have so we need an extra property, which is naturality again. So the interpretation of function space is first a function. Let's call it I don't know, beta. Okay, so a function beta. Sorry, maybe okay, let's call it beta. A function beta, which for every such morphism from J to I goes from A at J to B at J. And this also needs to be natural. So what does this mean? So I can take beta at F and alpha, and then I can restrict by G at alpha, and this should be the same as taking beta at F compose G and applying it to alpha, which is restricted at G, okay? So there's also a similar naturality square for this, okay? And I think maybe next time we should discuss how this definition comes up a bit more naturally if you define some general things for presheaf models. Okay, but this definition is valid, and now you can define, okay, and now you can define homework, define right restriction for pi, lambda, application, and the beta and eta laws. You also need to define this. Okay, this is the full definition of pi. If you showed all of this, then you have a definition for pi types in the presheaf model. Okay, are there any questions? Because time is up. So we only discussed how to obtain how the presheaf models support things that we already have in the meta theory, like natural numbers, sigma types, function space, and so on. And we haven't defined we haven't talked about the other aspects, how we can obtain things in the presheaf model from a category, and what does it even mean that a category has some things. So this, we will talk about this at next time, or the time after next time, and this will also be connected to a two-level type theory, which you probably heard about before. Okay, so I stop the recording. Okay. Okay, are there any